Hi everyone, this is Chapter 1, Section 5 on inverse functions. And we're going to start off with just an introduction, talk about what we already know about inverses and what we're going to learn about inverses. So let's start with the notation. We say if our function f of x has an inverse, so right off the bat we're saying not every function has an inverse, and we're going to talk about that later in the notes today. But if our function does have an inverse, we call it f inverse of x. That's how you'd say it in words. And the notation is right there on the slide for you. It's the little negative one. It looks like an exponent of -1. It's not an exponent. That doesn't mean f to the -1 power or anything like that. It means inverse. So again, the way you would say that is f inverse of x. Now, as just a quick description, this isn't the definition of an inverse, but it's a good way to think of them. Inverses undo each other. Whatever one function does, its inverse function undoes. So some very basic examples of inverses are things like adding and subtracting, multiplying and dividing, squaring and square rooting. Basically, you guys use inverses almost every time you do math. Anytime you solve an equation, you're using inverses. If we were trying to solve x plus 5 equals 12, and you said, okay, I'm going to solve by subtracting 5 from both sides. Well, you're doing that because of inverses. You're doing that because plus 5 and minus 5 are inverses, and they're going to cancel each other out. Now, what we're really focusing on today is more complicated inverses than just adding and subtracting. If we have a function that does several things, maybe it has a square root and a logarithm function and an exponent and something else in there, you have this big, messy, complicated function, what would undo all of that? Now, the reason that pretty much every math textbook that goes over this will put it in this order, you'll have one section in the book on compositions, and the very next section is inverses, because we use compositions to define inverses. So we just finished in 1.4, we just finished talking about compositions, and we're going to use those to prove that two functions are inverses. So if you do the composition of two inverse functions, the answer will always be x. And that's because, remember, if you take a number, x, whatever it is, and you plug it into one function, the function's going to do something, it's going to give you an answer. Well, if you take that answer and plug it into the inverse function, it's going to undo all that work and turn it back into x. And that's what a composition is, it's doing one function and then another. So this is what that concept looks like as an equation. Instead of me saying it in words, we say the composition f of f inverse of x equals the composition the other way, f inverse of f of x. So it doesn't matter the order this time. We said in 1.4 that compositions are not the same either way. This is one time when they are. It doesn't matter if you do one function and then its inverse, or the inverse function and then the original, the answer should always be x. So here are two pretty simple examples of inverse functions, x cubed and cube root of x. We know those are inverse. In fact, we use those. If I said solve x cubed equals something, you would solve it by taking the cube root of both sides. So what I want to do, let's use what we know about compositions to just plug in a couple numbers and see what happens. So let's find f of g of 27. And what that means is, what we want to do, really what I'm asking you to do here, is find this one first. Find g of 27 first. Then when you get that answer, if that answer is 10, plug 10 into f of x. So we're going to do this in two steps. I'm going to say g of 27 equals, now g is the cube root of x, so that would be the cube root of 27, which would be 3. Now since this was g of 27, we're basically putting it here for g of 27, and what I really asked you to find in this question is f of 3. Well, f of x was x cubed, so f of 3 would be 3 cubed, or 27. So you can see what I meant about inverses and compositions. If you're starting with a 27 and you do something to it, and then you do the inverse, you're ending up with 27. It turns right back into what you started. Now let's do one more just to show that it always works. We'll do g of f of negative 2. I switched the g and the f, and I threw a negative number in there. But we're going to do the same thing. We're going to do the f of negative 2 first. Now that would be negative 2 cubed, which would be negative 2 times negative 2 times negative 2, and that's going to end up being negative 8. Now again, just like before, we found f of negative 2, so we're going to put that in here. So what this question is really asking you guys to find is g of 8, which would be the cube root, g of negative 8, sorry, which would be the cube root of negative 8, which is negative 2. Remember, you can do odd roots of negative numbers. I can't do the square root of negative 8, but I can do the cube root of negative 8. And you can see it turn right back into the original number. So that's basically the idea of functions, looking at them as a composition. If you take any number, whether it's 27 or negative 2 or anything else, and you do something to it, and then you do the inverse to it, you'll be right back where you started, right back at 27 or right back at negative 2. So that's going to lead into our first real type of problem that you're going to see in the homework tonight. And that's how to verify inverses. And to verify means prove. It means I'm going to give you two functions, and I'm going to ask you guys to prove that they're inverses. Now the way you do that, you're going to do it using compositions, just like we did in 1.4. And you're going to do both of them. So again, if I call the functions f of x and g of x, which I usually do, but again, we talked about yesterday that the letters can change. If I call the functions f of x and g of x, if I want to prove that they're compositions, I have to do both. I have to do f of g of x and show that the answer is just x, and I also have to do g of f of x. So I have to show both of these things here. Now, if either one of them does not equal exactly x, then they are not inverses. So if one of them equals negative x, doesn't count, they're not inverses. Or if they both equal the same thing, but that thing is not x. Let's say you do f of g of x and g of f of x and they both equal 1, not inverses. Or they both equal x squared, not inverses. They both have to equal exactly x. And I said on here, checking one is not enough. Although I will say this, it's very rare for one of these compositions to equal x and the other not to. It can happen, and that's why we need to check it. But for the most part, if you try f of g of x and you get x, you're probably like 99% sure they're inverses. But we don't want to be 99% sure, we want to be 100, and that's why we do both. So here's an actual example. Here are two functions, a little bit more complicated than last time, just not just a nice simple x cubed and cube root of x. And we are going to verify that these two functions are inverses. So I'm going to do two compositions. Let's start off, and you can do them in either order. I'll just start off with f of g of x. So I'm going to start with f of g of x, which means I'm going to take g of x, which is that whole big function there on the right, and I'm going to substitute it right here for x. So basically I will have 2 times that whole thing, cube root of x plus 1 over 2, and then we'll have the, oh, and it'll be cubed because x was cubed, and then we'll have that minus 1 on the end. Now what we need to do is clean this up, and you need to show your work very carefully. When I say verify, it's basically a proof, and when you're doing a proof, you're not getting credit for the answer, you're getting credit for showing every step carefully. So a lot of times people look at this and they go, okay, I'm going to cancel this and this and this and this and this and this, and they just write equal x. You don't get points for that because it doesn't work. So for example, you have to do it in the right order. Like right now, if I tried to cancel the 1 from the x plus 1 with the negative 1 on the end, that's not going to work. You can't cancel something inside a cube root with something from outside of it. Same with the 2 and the 2. So we have to go in order. That's the key to this work. Now the one thing that will cancel is the cube with the cube root. I have a cube root function being raised to the third power. Those are the things that are going to get canceled. So I have 2 times x plus 1 over 2 minus 1. Now again, on this step, if you try to cancel the 1's, that's still a wrong step because one of them is being divided by 2. So you can't touch that. You can't touch something from inside of a fraction and cancel it with something from out. Now the one thing that does cancel here is the 2's. I am multiplying by 2 and I'm dividing by 2, so those will cancel. And what you end up with is just x plus 1 minus 1, and now those 1's finally cancel. And it did end up equaling x. So what I'm going to do, I'm going to put a little check mark here because that's what needed to happen. But remember, I said in the notes, if you stop here, you're not going to get full credit for that. I said at this point, like I'm 99% sure that those are inverses, but verify means 100% sure. So what I need to do, let's clear this out. I need to do the other composition. Here's my functions again. I need to do g of f of x and show that it also equals x. So this time I need to plug this function in for that x right there. So this time what I'll have is the cube root of, we'll have that whole function, 2x cubed minus 1, and then plus 1, and the whole thing is over 2. And remember, you got to do the steps in the right order. Don't try to do it all at once. You won't get credit for that. Make sure you're canceling the right thing. So right here, I'm going to focus on the numerator. I have 2x cubed minus 1 and plus 1. The minus 1 and the plus 1 will cancel there. So I have the cube root of 2x cubed over 2, and then those 2's cancel. I have a fraction where I'm multiplying by 2 and I'm dividing by 2. Now what's left over is the cube root of x cubed, and those cancel also and you get x. So by showing both of those, we have verified or proven that those two functions, f of x and g of x, are inverses. And now if you wanted to, you could rename one of them. You could call g of x f inverse of x. Or you could actually call f of x g inverse of x, because each one is the inverse of the other. So that's how you verify inverses. If I give you the two functions and ask you guys to verify or prove that they're inverses, make sure you're doing compositions like 1.4, and make sure you're doing both of them. You have to do each composition in either order, and each one has to equal exactly x. Okay, so if you're looking at the graphs of two inverse functions, this really kind of neat thing happens. They end up being a reflection of each other in the line y equals x, which is that dotted black line that I drew down the middle. So that line that cuts the first and third quadrants exactly in half, that's the line y equals x. So my original function in this graph would be the red one. That's the one that I labeled f of x. Without knowing an equation for it or plugging in numbers or anything like that, I could draw f inverse of x, the blue one, just using reflections. By doing a perfect mirror image of the red one over that diagonal line. Now, it's a difficult reflection to visualize. We're used to our reflections being either horizontal or vertical, like reflecting over the x-axis or over the y-axis, like when we did transformations. This is a diagonal reflection. It's a little bit harder to visualize, but remember, like I couldn't do it on the projector, but if you're working on paper, you can just turn your paper diagonally and just do a reflection up and down. It actually makes it very simple. So we have one last topic for today. We want to talk about what a one-to-one function is. And I want to go back to the very first thing I said to you guys. If you remember the first bullet point from the notes, I said, if a function has an inverse. And I said that because not every function has an inverse. And that's why I want to introduce one-to-one functions to you guys. That's how you know whether or not a function has an inverse. If a function is what we call one-to-one, then it does have an inverse. If it's not one-to-one, it does not. Now, the definition of one-to-one is kind of like the inverse of the definition of a function. So for a function, every input has exactly one output. For a one-to-one function, the opposite is also true. Every output has exactly one input. And that's where the name comes from. If you think of it as a group of inputs and a group of outputs, each one is matched up with one other thing, period. One input has one output has one input. These two numbers go together and they will never match to anything else. And that's what it means to be one-to-one. So a good quick way to tell if a function is one-to-one is by its graph. We can do what's called the horizontal line test, and you guys might remember the vertical line test from earlier years of math. If you're trying to decide if a graph is a function, you do the vertical line test. You say, if I can draw a vertical line anywhere that crosses it more than once, it's not a function. Well, remember when I described you, one-to-one is kind of like the inverse of a definition of a function? Horizontal line test is the opposite. It says if you can draw a horizontal line anywhere that crosses the graph more than once, then the graph is not one-to-one. So here's a couple examples. This is x cubed from our library of functions, from the first section of the book. And I said, this one is one-to-one. I drew in some red lines there just to show, I can draw as many as I want. There's no horizontal line anywhere that's going to cross that graph more than once. So it is a one-to-one function. Now this one is not one-to-one. I draw in that red line right there, and immediately it crosses more than once. So the parabola is not one-to-one. So let's do a couple examples using equations instead of graphs. So let's talk about f of x equals square root of 2x minus 3. And we're going to decide if it's one-to-one. Now, we want to think about the graph, and we want to decide if it's going to pass the horizontal line test. Now, I don't know exactly what that graph looks like, but I don't need to. See, I know this. This is the square root of x from our library of functions. Now, if I start doing transformations to that graph, well, first of all, let's just notice that one is one-to-one. I could draw in horizontal lines, it's never going to cross it twice. So the square root of x is a one-to-one function and has an inverse. But if I start transforming it, we got to decide if that's going to change it. And that's the question, the answer is no. If I were to take this and do a transformation like a stretch, that's still one-to-one. It doesn't change. Or maybe I shift it. I shift it over here. Stretch and shift like that. Still one-to-one. It's not going to change. Or maybe I reflect it like this. Still one-to-one. It's not going to change. So the idea is the basic transformations aren't going to change if your graph is one-to-one. That means as long as you understand the graphs from our library, any square root graph is going to be one-to-one. So the final answer to the question, that was a long explanation, but the final answer to the question is yes, it is. And that means it does have an inverse. So now let's talk about this one. F of x equals x squared minus 5x plus 7. Now, same concept as the last one. I don't know exactly what it looks like, but I do know it's a parabola. And a parabola, we already decided, fails. It's going to fail the horizontal line test. It's not one-to-one. Same rule for transformations. If I take that parabola and I reflect it, that still fails the horizontal line test. Or if I reflect it and I shift it, maybe it's starting here and going like this. No matter where I put it, it's always going to pass, it's always going to fail the horizontal line test. Cross 1, 2 spots here, cross 1, 2 spots here, cross 1, 2 spots here. So basically, every parabola fails the horizontal line test. So without even knowing what the minus 5x plus 7 does, The answer is no, this one is not one-to-one and does not have an inverse. Now this is actually going to end up bringing us to the end of part 1 of notes. I'm splitting this into 2 days. On part 2, we're going to talk about how to find the inverse. So today I gave you 2 functions, f of x and g of x, and I said let's verify that they're inverses. On part 2, I'm only going to give you one. I'm going to say here's f of x, find its inverse. And the first step to that process is going to be this right here, is you guys deciding whether it even has one. If it's not a one-to-one function, then you just say it doesn't have an inverse and you're done with the question. And that's where we are right now. We know how to verify if 2 functions are inverses. We know how to tell whether or not a function has an inverse, but we haven't talked about how to find it, and that's for part 2.